Okay, as a last thing before we go on break, we're going to continue talking about optics. And so I'm going to start with just a review question about, don't have to do a calculation, but what relates to what. So the image of a pencil produced by a single mirror is virtual. Which statement must be true? Which line? There are multiple ones. Must be true. We'll go through these one by one. Actually, before we go through one by one, let me make sure we remember what it means to be virtual. What does it mean if it's virtual?
It means it's not real.
It means it's not real. That is an absolutely correct definition, although it probably wouldn't be the one on the test if I were to ask it on the test. Yes?
Is it like when the proportions are wrong?
No, that would be out of focus.
Okay.
It's a what?
False focal point.
False focal point. Well, because I'm talking about virtual image, it's not a focal point. It would be.
When it's on the negative side.
If you had parallel rays, their image would be a false focal point. You call it.
Did that have to do when you said that the lines itself don't cross or whatever?
Okay, that's the definition that I would be looking for on the test. A virtual image is the image where the rays don't actually cross, but the projections of the rays cross.
Oh.
So the observer sees these rays and their brain says, well, they just go back until they touch here, even though they didn't actually meet there. Yeah, which is why behind the mirror was correct, because they can't meet it behind the mirror. Yes, Ryan?
It's the projection of the reflected ray.
Well, we have them both with mirrors and with lenses.
Oh, true.
So that's why I don't say yes on that, because we have it with both. But if it's a mirror, then yes. The projection of the reflected rays. If it's a lens, it's a projection of the refracted rays. So if the question I had asked, obviously this one is a mirror. If the question I had asked was, what is a virtual image from a mirror? Your answer would have been 100%. Okay, so now that we've clarified that, does the mirror have to be concave to produce a virtual image? No is correct. No is correct. Remember, I used both of these, and he had a virtual image when this was close enough to him, and he had a virtual image always with this one. So you always have a virtual image with the convex mirror, and you sometimes do when the object is closer than the focal length, then you have a virtual image with the concave one. So it is not required to have concave. It's likewise not required to have convex. It works with both. Convex only produces virtual, but concave produces both. Image distance is positive. Obviously, the next two are opposites. Image distance is positive or image distance is negative. Uh-oh, we've got disagreement. This is where we have them argue it out in detail.
Well, I feel like the concave one, whenever it's a virtual image, it's positive. Because it's on the same side. Whereas for the convex one is negative.
I think it's positive.
No, remember the rule we started with. It's where you have the projection of the rays meeting. The rays really exist on the side where it's reflected. And so you would have a positive image distance if you have a real image because it's on the right side. If it's the projected rays, then you have negative. So anytime it's projected rays, it's going to be negative.
Side.
What?
There's no rays on a negative side.
Right. Well, for a mirror. For a lens, you have them on both, and you have to be more careful. Because light goes through. So because it's projection, it's a negative image distance. So this one here, image distance must be negative if it is virtual. And then the image upright or inverted. Once again, you can think about the experience with Wesley. It's upright. The virtual image, if you have a single lens or a single mirror, is upright. A real image would be inverted. So without having any numbers here, the fact that it was virtual tells me that it's located on the other side of my mirror, since it was a mirror, with a negative focal length or negative image distance, and that it's upright. First trace, then mirror.
Okay, so you crossed off B, but to the question asked, B seems like a correct answer, and I don't understand why it's not.
Okay, it doesn't have to be convex. I could also make a virtual image with concave. Now, if I said I have a convex mirror, what type of image does it produce? Virtual would have to be the answer.
So it says the image of a pencil is produced by a single mirror is virtual. Which of the following?
Must be true. Right? I mean, could be true. This could be true. This could be true. But neither must be true. Mirror.
So if a real image is inverted, is that why our eyes, like the images that we see, are actually upside down and our brain has to turn them right side up again?
That's correct. And this is one of the coolest psychology experiments that I've heard of. You've heard of it too?
Yes.
I talked about it with sound, didn't I?
Yeah, I've heard before that, but yeah.
But yeah, do you guys remember me talking about this? I don't want to bore everyone.
I don't remember.
Okay. Andrew does it, so we'll do it. So they tested people's hearing first. Actually, first. I'm sure it was two different, completely unrelated experiments. But they tested people's hearing by using fake ears. So they put an external ear made out of a kind of plastic. The way you do your location on where a sound comes from is based on how the sound reflects off of your ear. And so basically you've learned to interpret the shape of your ear, which is really weird. One of the things I used to love to do in class is have somebody close their eyes, and like you close your eyes, you snap your finger, you say, point to where I snap my finger, and they point right to it. And then you say, okay, now bend your ears down like this, and you do it again, and they're way off. Because the sound is reflecting differently with the bent ears, and they interpret as different location. So they gave these people prosthetic ears to wear, and over time they learned how to identify where the sounds came from so they could tell with these prosthetic ears. And I said, okay, so you can learn. And then they took them off and they tested them. And what they found was they could still tell where things were when they took them off. So basically they learned a new skill. Now with the vision test, they fixed people up with glasses that had prisms to invert the light. And so initially people were trying to eat and they're, having a hard time getting it into their mouth because they see it below, and so they raise it, but it's inverted, so it was actually above and they needed to lower it. And so after a couple of weeks, they learned how to deal with it. They have videos of them riding bicycles, which has got to be hard if you're disoriented. So they learned how to do it. And then they took the glasses off. And then they're having a hard time eating again. So in that case, with the visual system, it wasn't learning a new skill, it was adapting. And then they had to adapt back. Which, okay, I just think it's a really cool psychology experiment. Telling you about neural pathways and how learning is different. You guys have heard about different learning styles. Well, the way we visibly process things is clearly different than the way we audibly process things, as indicated by that experiment, or that set of experiments. Now, I went through these ray tracing diagrams yesterday. I have them again. I'm not going to go through them carefully this time, but I have them here as a reminder. On the exam 3, you will have to use a ruler and do a ray tracing diagram. And your grade will be based on the accuracy of your drawing, not on having the image in the right place. Everyone should be at that point able to calculate where the image is perfectly. That's not what you're going to be graded on. It's if your rays are correct to find the image. So the keys for these ray tracing diagrams is the image is located where all of the rays that leave one point in the object come back together. So there's rays leaving the tip of this pencil in all directions. We only show 3, but obviously, and I said all, I should have been a little more careful on that word. Obviously, there's more rays. There's rays going like this and like this and like this. Not all of the rays are going to contribute to the image. Only the ones that go through the lens. But a ray that goes like this is going to come down and go through that point. A ray that goes like this, it's going to kind of come like that and go through that point. So all of the rays that go through the lens are then going through the same point to make the image. Yes, Mira?
So if we define where the real image is, how do we know what angle to draw them at, if that makes sense? If we have to figure out where the image slopes.
Yes, it makes sense. The answer is we only choose 3 rays that are easy to do. The other ones are not easy to do. Right, the top ray and the bottom ray that I did, I can only draw those because I know where the image is.
Yes.
Without knowing where the image is, I would be out in left field.
Yeah, that's why I want to ask. How do you draw that if you don't know exactly where the real image is?
Right, so we take these 3 here that are easy to do. And so that's where we have to know what these 3 are. The green one here is the parallel ray. And the parallel ray starts parallel to the principal axis. So here's our principal axis. The parallel ray starts parallel to the principal axis, and then when it gets to the lens, remember we're taking the thin lens approximation, which says that all of the curving, all of the refraction occurs at the center of the lens. Untrue. It's going to refract first at this surface and then at that surface, so it's actually going to come out at a different height. But we're making the approximation that it comes out as if it's a very thin lens. So when I do my ray constructions, I draw this center line, and that's what I use for my lens. Go ahead.
But how do you know how much, when you're drawing it, how much to bend it after it goes?
Okay.
That's what, yeah.
Continuing on then.
Well, I think if we know the height of the object and then we set it on that line,
Mhm.
we'll know where it'll end up.
Well, you have to know the focal length as well. And that's what Mira is asking. When it goes through here, a parallel ray, by the definition of the focal point, will refract and go through the focal point. So that's how you know how much it's going to bend.
Okay.
So the parallel ray comes in parallel to principal axis, and by definition of the focal point, it will bend and go through the focal point.
Okay.
Then the second ray here, the red one, is the vertex ray. The vertex ray is like the example we did where we had a pane of glass, remember last class period, and we had light that came in, refracted, and then came out parallel to it. We had to show that it came out parallel, remember? If we have parallel surfaces, it will come out parallel. Now, it was shifted a little bit, but in the thin lens approximation, that shift is 0. And so the vertex ray is just going to go straight through because it's parallel sides on where the vertex is. Yes?
So how are we gonna know, like right there, the F, how are we gonna know the distance? Do we just?
That's going to be given to you.
Oh, it's gonna be given. Okay.
Yeah.
And it's gonna be half on one side, half on the other, and then you put that middle one?
No. This, you will draw everything, and I'll tell you the focal length is this and the object distance is this. That's all the information you get. If it's a positive focal length, then that means that it is a convex nature lens. Negative focal length, it's a concave nature. So positive focal length, here's your principal focal point, and here's your secondary one, or I think Sarah called it the virtual one, or what did you call it, Sarah? Don't remember? False focal point. Okay. So if it's a positive focal length, you have here for the principal one and here for the secondary one. If it's a negative, you would have them reversed.
So
That's an important factor.
the way you space them to know exactly, like, are they gonna be
It's
like?
done with a ruler.
Yeah, but what I'm saying is the two Fs, are they like equal distances?
Yes,
Okay.
yes. Once again, for the thick lens approximation, or thin lens, approximation. Okay, so the parallel ray, the vertex ray went straight through, and then the last one, the focal ray, goes through the secondary focal point, and then once again, because the definition of the focal point, light that goes through the focal point is going to come out parallel, because light works the same forward and backwards, so a parallel ray in here goes through this focal point. So you know exactly how to draw those 3. Any else, no idea. But those 3 you know how to draw. And so where they all three come together, that's where the image is.
So in the beginning, that ray one, it's parallel, and then that's when it bends, and then the other one, it's reversed. It's like
Right. Ray 3 is the reverse of ray 1. By the reverse, it's parallel on the opposite side going through the focal side now. So parallel to focal or focal to parallel. Okay, so you have to know those are a converging lens. A diverging lens, you have the same rays, but it looks a whole different. So same rules. Ray 1 is parallel. The parallel ray should exit and go through the focal point. But the focal point was back here. It's a virtual focal point, right? And so the exit ray, we have this drawn as a dashed line because there's no light actually there, but it comes out as if it came from that focal point because it's a virtual focal point. Then we have the vertex ray, which just goes straight again. The vertex ray is the easy one. Don't get that one wrong. And then we have the focal ray, and the focal ray is probably the most confusing one because that's the one that goes to the secondary focal point, but now the secondary focal point is on the opposite side. And so this blue ray is going toward the secondary focal point, but when it hits the lens, it comes out parallel because if it goes through the focal point, it comes out parallel. So it never makes it to that secondary focal point. And so you notice, in this case, they just changed to a thin black line for the extrapolation. Remember when I did it in class, I erased the line so it wouldn't confuse us. Because oftentimes people will try to make the image with this, when that was only really to guide them on, did I draw this line in the right direction? So you have these three rays. If your eyeball is over here, if your eyeball is here, you see that light coming out, and your brain says, yes, those must have met. They must have met back here. They didn't really, so it's virtual.
So if we were to get something like a diverging line, do you want us to draw also the dashes to, or?
I certainly would myself, because that's the only way I'm going to get my line straight. What I want you to do is to do it correctly. So do it the way that allows you to do it correctly.
So do you want
So this here is not part of the technical construction. If it's not there, I'm not going to mark you wrong. Right? What you need to have is what you have in green, blue, and red. But make sure you do it right. So if you're like me and you need this to do it right, do it. But don't get confused and try to put the image over here. Wes?
Doesn't the bottom ray have to go through the focal point? Or
By the bottom one, you mean the red one?
yeah.
Okay, so the red one is the vertex rays going through the vertex. And so that's the point where the sides are parallel, so just go straight through.
So the focal
It's confusing because you tend to think that this blue line might be the principal axis, right? But it's not. Being careful here is really important because it's easy to make mistakes. Yeah.
So the focal ray always goes to the secondary focal point, right?
The focal ray is always the secondary focal point. That is correct. And so when it's a when it's a concave lens, then the primary focal point is on the same side as the object and the secondary is on the opposite. If it is a convex, then the primary is on the opposite. And it all comes back to a convex will bring the light together. And the sign convention works for you. If it's a positive focal length, for a lens, it's going to be on the right side. If it's a negative focal length, for a lens, it's going to be on the left side. That's because in our convention, you don't have to follow conventions, but it makes so you make less mistakes. In our convention, we always have light going from left to right. Of course, if you have a mirror, it starts going left and then it reflects back, but that's our convention. So everything I've done, I think, has followed that convention. Any more questions? I mean, I sincerely want you all to get this right and to understand it. Okay, moving on. I have 3 slides here that are geometry slides. You may or may not understand the geometry. As with what I did in class on Tuesday for the calculus people, I'm not going to test you on the geometry relations here, but I want you to see that there's actually a reason for the conclusion that comes up. So this here is showing two of the rays for constructing an image. What do we call these two rays? What's the top one called here? Parallel ray. And what's the lower one called? Vertex ray. Excellent. So we have the parallel ray and the vertex ray. Only two rays here. Why do I require three? Why did we have three in the previous one? Because if all three agree, you have pretty good reason to have faith. If only two agree, well, any two lines are going to cross unless they're parallel, so you're always going to find something, but it may not be the right thing. So that's why we do three. This one here is just for geometry. And so what we're going to look at on this picture is two similar triangles. That triangle. Of course, I didn't draw the opposite sides on either of these. I only drew two sides. But those triangles are similar. Why are they similar? This angle's the same. This angle's the same. And if any two angles are the same, you know what the third one is? The same. So this is your angle, angle, angle triangle. Angle, angle, angle triangles don't have to be identical, but they have to be similar. And so in this case, tangent, because it's a right triangle, tangent of alpha on the left side is the height of our object divided by the object distance, which this wrote P, so I'm going to put DO here. So we have tangent of alpha is H over DO. If we look at the other side, we have tangent of alpha is the height of the image divided by the distance image. There's a minus sign thrown in here for a good reason. If the image is inverted, we say the image height is negative. So that's why we have the negative there, because H prime is negative in this picture. Tangent of the angle is going to be a positive, so that's why we do the negative there. So it's correct and important. So this relationship tells me a relationship between the height of the object and image and the distance for the object and image. Now we define magnification I used I for image here, and I had H prime on the other one. I'm sorry, it's HI and H prime are the same thing. So magnification is defined as the height of the image over the height of the object. In this case, the image is inverted, which means the magnification is a negative value. So negative magnification, inverted image. Positive magnification, upright image. We've learned some more things. If it's a negative magnification, is it real or virtual? It's inverted, and inverted images are real. So a negative magnification is going to tell you, oh, that's a real image, if it's a single lens or a single mirror. Positive magnification means it's virtual. Then we have the height image over height object. If height image has a bigger magnitude than height object, then it's enlarged. If height image is smaller, then it's diminished in size. But if we look at this relationship, if I take this and I solve it for, so I'm going to rewrite that H over distance object, height object over distance object equals minus height image over distance image. I prefer using I's and O's and D's. You see, this came from a different textbook that used P and Q and H prime. P for object distance, Q for image distance. You should be aware that you will see different nomenclatures. As long as you're understanding what you're doing, the symbols isn't a problem. But if you're unclear, it can be a big problem. So based on this relationship, if I take both sides and I multiply this by distance image, divide it by minus height object, and do the same over here. Okay, I should have used a different color for that. Different color so you can tell what's the add-on. Hide, edit, color, red. That's not red still. I'll do that while I'm at it. So I put in red the same thing on both sides, so it's legal. And then my height objects cancel, and my distance images cancel. And I have height image over height object equals minus distance image over distance object. But that's the definition of magnification. This is something you need for the homework that's due tonight if you haven't done it already. The magnification is height image over height object, or minus distance image over distance object. So I hope everybody can see, yeah, that wasn't a big geometry jump to get this relationship. But what you have to be able to do is to use, is to use this relationship. And know that there is a legit place it comes from, that it's not just pulled out of thin air, right? What good does it do you to just have a bunch of equations? The teacher said it's true, so it is. That doesn't really help me much. So we've already gone through that. Now our next diagram. This one here is going to not look at alpha, but instead look at just beta on the image side. And so in this case, we have two triangles that are once again similar triangles. This has a height that's height of the object and a distance that's focal length. And then the next one is going to be this here, which is distance image minus focal length. And this here, which is going to be, I'm going to put minus h prime or minus h image here. The reason I put the minus sign with it is because it's inverted. And so just like before, tangent is opposite over adjacent. So I'm going to have h over f is equal to minus hi over di minus f. So h over f equals minus, and yeah, I'll write it the way I like it in a color that you can read. Now, this isn't the magnification, but this is a useful equation. How is it useful, you ask? Are you asking that? Good. Great. It's either that or no, I'm not, I don't care. I prefer if you care. Well, I can take this and I can say, we know that height image over height object is the magnification, which is minus distance image over distance object. Solving this equation up there in black for height image over height object, I'm going to have, and I'm going to actually write it, I'll write it up here. Come on, seriously? Okay, so there, I just quickly solve this for height object over height image. Now, my equation here, I have height image over height object. So I'm going to, and did I forgot a minus sign, didn't I? There's a minus sign right there. You do have to make sure you don't make that mistake. So I'm going to just invert that. So this is equal to that. And at this point, most logical people are saying, I don't think he's going anywhere. I mean, he's got an equation, but it doesn't look familiar to me. Well, we'll rewrite the equation and get rid of both of the minus signs. So I'll have distance image over distance object equals distance image minus f over f. So the two minus signs that disappeared were this and this. And then I'm going to take the right-hand side and say, well, that's distance image over f minus 1. The last step to make this useful is to, well, next to last, divide everything by distance. Divide all the images, I'm 1 over f minus 1 over distance image. And that's an equation now that rings a bell. We usually rearrange it to solve for 1 over f equals 1 over distance object plus 1 over distance image. And what is another thing you learned in lab for 1 over f? Power. So that's the other equation here that you must be able to use. And I want you to know that it has a legit basis, that it's not just some random thing or something arcane, something that came from not super complicated geometry. Any questions about these two equations? You know you don't have to derive them, but it's important that you understand how to use them. So this is just going through the math. Let's do a problem. So let's pull out a piece of paper and work this out. A 3 centimeter tall object is placed 19 centimeters from a 25 centimeter focal length. First thing to do is to draw your principal axis. Nice job, Nate. And then draw your lens. And notice I just drew my lens as a vertical line. Then identify your, and I went through all these steps. Was it in class on Wednesday? Or was it in lab? Okay. Put your focal length. So our focal length is 25 centimeters. Is this a positive or negative focal length? Positive. It would have had a negative sign. It doesn't say plus 25. It doesn't say it has a positive. It says it has a focal length of 25, and you have to say, ah, that's positive. And so this is your principal and secondary focal points. And then finally draw your image. There's my image. Or object, excuse me, object. Now you need to find where the image is formed. Can anyone, without doing any work, give me an idea where the image is going to be formed? This is a lens. Where's the image going to be formed? Okay. We have an answer on the left side. She is correct. Now do the work to show that Leslie's correct. You guys need paper? I got paper here.
We have one. Not that one, we're not using that one.
This was the last visit.
Doesn't matter, we're reading
Well, you have the object and there's only one image position, so don't draw the image until you find it.
Oh, true.
And you tell me which ones are better, mine or his on mine.
Yeah, we're looking through lenses.
You have an interesting prescription.
Nobody knows.
We're doing the lenses.
It's just blue screen, so I.
Direction is to the right. Sorry.
So the one. So we defined
Oh, mine are first. So
this to be right to be right, so the left to be left.
Yeah.
So he doesn't use it, then he
Those are some stuff you're the image.
Oh, so yeah, that's the image that you made last week.
Put mine on and
I'm
then.
talking about the object itself.
Yeah.
It's gonna be on the right side.
It's like.
This is at 19 centimeters.
The object, so the object.
The object
is
is
the green arrow.
on the left side. Is that what you're
It feels like.
That's what I was trying to figure out.
By convention, I drew it with the object on the left side. If you drew it with the object on the right side, you just be reversing it.
You what? They're progressive. All the fish. They're both bad. They're both the same. And you're right, your eyes are.
No, maybe.
Right.
No, the left eye gets zero to better. And the right eye actually either the same or worse, some worse.
Let me see.
Well, once again,
Let me think my has.
the lens itself is convex, right?
Oh, I don't know.
That determines how the arrow goes. The last one's kind of weird because it goes in the direction of the secondary fault. And then it goes to arrow.
You're sending it.
Oh, that's better.
She's so sad that there's nothing to do. No, she said not to even text her because, well, obviously it's a lot. Is it going to be on the right side and then on there's only 73?
Ryan, we should plan these things. This is what you're doing. I'm serious. I think this is what we should take. And then let's make that.
What type of lens is it?
Okay, I have a question. What type of lens is it? Its focal length is positive. What type of lens has a positive focal length? A convex lens.
That's what
Oh.
Okay, so this is how it
So this one here is not
this would be the parallel one. This would be the vertex. And this is going to go and it go down. It goes through. And it'll keep going until it hits the lens and then it's going to go parallel. Which obviously my wife What's the blue one?
I'll go back to the blue one.
It's all starting to bind. The thing is, normally the object starts here. So the green one will go through here and then go straight on the blue and the red are both The blue one and the red one are both.
Oh, this is a lens, not a mirror.
The green one is not going to connect at all because it's in front of.
Well, are we done?
No, the object is in front of the right?
Okay, yeah. If we sent it.
Sure, that's funny. They like really down the wrong thing.
I don't know if I said the problem. Has Leslie done it? She has a nice looking diamond.
No, because I realized that I forgot to, that I was thinking of the other one. And when you have to draw the little dots to try to figure out where the virtue is.
Yeah,
Yeah, I realized
she
I was
she-
doing the
she-
first
she-
try.
Okay, I see a lot of people working in different directions on this. Given the time, we're not getting to mirages today, guess what? But I will now go ahead and work the solution both graphically and algebraically. So I'll start with graphically. What are the three rays I draw? Name one. Parallel. So the parallel ray comes out of this and goes parallel to the principal axis. Then how does it refract? Through the focal point. Okay, what's another ray? Vertex. Vertex ray goes from the tip through what point? Okay, the vertex, which you call the origin, that's fine. Okay, wasn't close enough for me. That was a little closer, and it's going to have to work. What's the third ray? And now we say row, right? Because which focal point is this supposed to go through? The secondary one. Well, that's here. But my light is going to the right. So I drew a dashed line for the beginning part. And so that's the ray as if it came from the focal point. How does it come out when it hits the lens? Parallel. DJ's got these words down. So there's the light coming out. Where do those meet? Okay, they never do is correct. So now I'm going to shrink this down to try to get something where I can make it close. Okay, that probably wasn't great, but we'll see what happens. Yeah, it just took a little bit with me. I'll have to fix the equation when I come back. So now I extrapolate these back. So I'll extrapolate back and extrapolate back. That's not the color I meant, but it'll have to do. Extrapolate back. And they all meet here, so there's my image. Is that real or virtual? Virtual because? Okay, it's the extrapolated lines. Is it upright or inverted? Upright. The arrows point up in both. And as a final question, is it enlarged or diminished? Enlarged. That was obvious. Obviously, without using a ruler, you're not going to get the right position. So that's why we like to use the mathematical equation. And so I'm going to identify my values. There's F. There's distance object. So 1 over F equals 1 over distance object plus 1 over distance image. Solve that for distance image. 1 over distance image equals 1 over F minus 1 over distance object. Put in my numbers. 1 over 25 centimeters minus 1 over 19 centimeters. And so now I have to get out a calculator. 1 over 25 minus 1 over 19. I cannot do that in my head, friends.
That would be about negative 0.01263.
Well, thank you. Units of centimeters to the minus 1. Well, now I have to invert that. What do you say? 0.01263, 0.0. Yeah. All right. That's the first time that's actually worked to my advantage. But I still have to do it in the calculator to get my final answer. So Oh, and she did it wrong. She must have misheard me. Oh, wait. I hit a plus sign. Forget that. She might have done it right. Yes, ma'am. No, she did it right. Okay.
I don't know what you call that, the little line on it. How did you know to draw it like up instead of having it cross down and then parallel?
Let me finish this calculation. I saw that somebody had this number, so kudos. There's the distance image. Okay, so the question that Leslie asked was, how do I know which one? Name a color to start me off.
The brown one.
Okay, unfortunately I did too much brown. But you're talking about this line here.
Yeah, how did you know to draw it up instead of having it cross going down? That's what I'm saying.
Okay, so what we are supposed to have for the focal ray is a ray that goes from the tip of my object through the secondary focal point and hits the lens, right? That order is not possible in this case. And so we reverse the order. We say if it goes tip, focal length, lens, it actually has to go focal point, tip, lens. Because it needs to be a ray, right? If it's a parallel ray, if it was a parallel ray like this, it would come through the focal point. That's the rule we're matching. So what we really need is a ray that goes from the secondary focal point to the lens, and the tip of my object is also on that ray somewhere. That's what we need. And so I take the tip of my object and the focal point, secondary focal point, and I draw that line and continue it. But the light didn't start at the focal point, and so that's why I had dashed lines up to the object and then continued on that line with a real line because the light really traveled there. But it's a very good question, right? It's the confusing part here. So, a real problem, we solved it two different ways. And I looked around and most people were having some difficulty with this. So, at this point is the time to ask questions to clarify difficulties. Wesley.
So, negative distance is not always to the right of the lens.
The negative distance is going to be to the left.
So it's dependent on
It depends if it's a lens or a mirror. For a lens, the light is supposed to reflect. So for the reflection, positive is on the same side as the object because it's reflecting. For a lens, because it goes through, positive is on the opposite side. So the way I try to describe this to make it sound reasonable is there's a side that the light's supposed to go to after it hits the object. That's the positive side for the image. So if it's a mirror, it's supposed to reflect back, so that's the positive for the image. If it's a lens, it's supposed to go through, so that's the positive for the image. Other questions? Thought that was a question, Chad. So do you feel more confident with this? Good. That's what I shoot for in class. Mirages. Mirages are caused by refraction. The same thing that makes a lens work is what makes a mirage. And the typical mirage you see, so here's an actual photograph of a mirage. This here looks kind of like water. And then if you look here, you have what looks like a reflection of the tree down below the horizon. It's not really a reflection. It's refraction. It's like Ryan's read my slides already or something. This stuff here that would have been blue, what is this blue stuff? I know, black and white picture, you can't tell it's blue, but what is it? It's not water. You've seen Bugs Bunny disappoint so many times, you know it's not water. It's sky. Somebody said sky, I think. That's the sky you're seeing. Why does it look like water? Well, it's blue, and it looks like it has ripples. It looks like it has ripples because you have hot air, and hot air expands, and expanding air is less dense and rises. And so you have air currents there, and the air currents are causing the air to move, and hotter air has a lower index refraction, closer to 1, my goodness, closer to 1. And so different refraction for different temperatures is why you see it kind of waving. And so this here is a diagram to show you how you calculate the angle of incidence and angle refraction as it's going into hotter and then back into cooler air as it comes back up to give you a mirage. So that's the traditional mirage. Here's a different kind of mirage. Here you have, that's a line in the sky, and you see that building up in the sky and upside down. This occurs usually over bodies of water where you have an inversion layer, where the air is cooler over the water and then it gets hotter as you go above. And in that case, you have the same effect of as it gets into the hotter air, it's going to bend and comes back down. And so you're seeing that house inverted and up in the sky. So that's how mirages work. That's where we stop. Have an excellent spring break. Mira has a question. Will there be a homework assignment is a good question. I'm going to go with no because the test on Tuesday. No, there's no homework on Monday.